Our next speaker here is Jeff Grunewald, and he's going to be talking about event-based distributed Elixir. Give it up.
Hi there. Yeah. My name is Jeff Grunewald. I've been working in Elixir now for about 3 years, and of late, I've been doing a lot of work with data processing, all things data processing, and to be able to accommodate some of the needs of the project that I've been working on, we chose a microservice architecture distributed in a Kubernetes cluster. And so today I'm going to be talking about some strategies that we have taken and things we've learned about how to do that sanely and safely so that you can follow along at home, and how we've encapsulated that into a library that we wrote called Brook. It's an event stream joke, or the microservice actor, which I'll get back to in a minute. So first things first, most people here have probably heard of microservices and have a general concept of them, but let's take a look at what they mean in abstract real quick. Does anybody recognize this guy? So if you're familiar with MASH, this is Major Charles Emerson Winchester III, and he was famous for saying, "I do one thing at a time, and I do it very well." And that's what I like to think of as sort of the distillation of what a good microservice is. If you've heard the joke, a microservice can't fail because then it's doing two things. So this is what we shoot for when we're trying to design a microservice architecture, and we want to separate the concerns out into as small components or pieces as we can. We can easily reason about them, and we get a lot of benefits for that if we do it right. So what makes a microservice? So they're discrete components, obviously. They do one thing, ideally. And some of the benefits, you get to modify and version and scale them independently of each other. So that works at deployment, at runtime, but it also works in planning. You know, if you have a team that can accommodate working on different components of a system in parallel, having your application designed well in microservices allows them to do that and not be stepping on each other, not waiting on each other to, deploy new things or merge things in. You get to go a little faster. They're distributed across a network, and that could be locally, right, on your desktop in Docker containers or in different terminal windows, but it could also be globally across any number of regions. And now we have state to worry about, and we'd like to be in a world where we deal with entirely stateless microservices, but the reality is that's not feasible. At some point, state can't be pushed any further to the edge, and you have to deal with it. But they should never share state. They always want to be independent of each other so that they're not blocking each other. You're not single-threading their interactions with the system as a whole, and you don't want them to accidentally be modifying state out from under each other. And they're going to be communicating by sending messages over the network. They need to do that to interact, but they also need to reconcile different views of how they see that global state. Does this sound familiar to anybody? That's me, by the way, usually online, if you can find me. Fry is my spirit animal. So actors, they may modify their own private state, but can only affect each other indirectly through messaging. So what we're looking to do here is expand the actor model that we're so familiar with from our Beam processes out to the level of the service or the component layer. And we want to have the same rigor in how we design those interactions so that our applications can operate safely and efficiently. Now, this comes with some challenges, right? You're communicating across services, and that can be many services, especially as your program grows in complexity. So they're going to be communicating in parallel. They're going to be doing things at different rates, different speeds, and they're going to be doing it asynchronously. Again, they're going to handle these operations at different speeds based on the complexity of the calculations, network latency, load on different components, especially ones at the edges of the system. And you need to be able to account for that, and you don't want any of them to be blocked if you can help it at all possible. You're going to be broadcasting messages to the entire system, right? It's no longer efficient at this stage to be directly communicating from one process to another because things are going to happen somewhere either in the system or outside of the system that's relevant to lots of them. And you're going to get bottlenecks if you have to wait for one service to pass a message down the chain to the rest. You want them all to be able to react, if at all possible, as soon as they see an event that is meaningful to them. Has anybody tried using A/B cast, multi-call? Quick show of hands. I see 2. I've actually never used them. I stick to the traditional cast and call myself. And another thing to keep in mind is not everything runs on the beam yet. We're getting there. There's all kinds of dependencies, data stores, caches, machine learning libraries that you may have already invested heavily in Python or other languages, and you want to be able to interface with those and ideally maybe supervise them with your Erlang or Elixir processes. And so you want to be able to interact with those in some form that is not tied directly to process messaging. And again, when you're talking about sending messages over the network and they're not able to do that direct process-to-process communication, there's probably a little additional network overhead now because you have to drop down to a heavier weight network protocol to exchange information. And this gets complicated. Start to look like something like this. And before long, you're in our shoes and you've got Kubernetes. So how do we do this at a high level? How do we want to approach this problem? And there's 4 steps. So the first thing is an event bus. And this is another one of those all old things are new. Again, this is an old enterprise architecture strategy. And you have a pub-sub broadcasting system. And the different components of your system subscribe to some channel or topic or queue where this conversation between components is going to be taking place. And they can react, if necessary, to anything that happens to go along in there. So your Kafkas and your RabbitMQs come to mind. This provides you a unified view, you as an operator, you as the manager of the system, a unified view of that state that is independent of any of those single services. And one of the added benefits that this gives you is replayability. So if your system crashes, if you have some catastrophic failure, you can go replay events that you've logged and stored back through the system to recover. Or you can hydrate a test environment or a staging environment to validate changes aren't going to break the system before you roll it into production. You just grab the events most recently out of your production environment and replay them right through that other environment, and you're good to go. So the next stage is an event contract. You want to know roughly what you want, how you want to structure the messages that these events are going to be communicating in. And so this is minimal, it's fairly lightweight, but it gives us the ability to assert what we're passing and be able to trace that, those events based on what information we do include and we do think is important. So we have an event type, right? Like this is going to tell the event the context that it needs to know to act on the information in it. You've got the author or the source application that generated the event. You've got a timestamp. And we have a concept of forwarding because we want our solution to be multi-process architecture capable, so we can distribute it across multiple instances of a given service. And at the same time, they still have to share state between logging aggregator 1 and logging aggregator 2. So we have the concept of forwarding. If this message was handled by node A, it forwards the message to node B. Node B has the information. It can take action if necessary, but it doesn't write that to storage. That was already handled. And then in the middle here, you've got data, which is your generic term. And you'll probably want to stuff something fairly moderately complicated to give all of your applications the information they need, the full context of that specific event. So you're probably talking about a map or ideally a struct. Which brings us to step 3, serialization. So this is going to be your interface to the message log, the message queue system. It's also going to be how you are able to interface these components with non-beam systems. But it's also going to allow you to store that event data in the application or the component's view of state. And I'll come back to why that is important in a minute as far as serialization. And we're going to use JSON again for this because it's the universal language for interchange between languages and platforms and components. And finally, we've got the view state, which is, in my opinion, it's sort of the unique component to our approach here, which allows any given component or service within your system to track only the events that that component is responsible for. It can ignore the rest safely. but it also stores only what's needed. So if we want to minimize the need for these different components to share some sort of back-end storage resource, we want to be efficient in what they need to store. So they're going to pull apart that data block of an event. They're going to store only what's important to them, and they're going to let the rest pass along to the rest of the components in the system to do the same thing. And once again, this allows us to be independent of each other. And you can grow your system, evolve it, add new components. And as long as you're thinking about that contract and the pieces of information you need to put into that data key in your message struct, you can grow very gracefully. So now we're going to talk about Brook specifically. So Brook is modular. That's the first thing. A lot of the stuff we designed with extensibility and customization in mind, giving the user the ability to swap out the parts that they want with the parts they're familiar with, they don't want with the parts they're familiar with, the parts that they already have. So just because we chose Kafka and Redis, largely for speed, Kafka for throughput speed, and Redis for development speed, it's just easier to work with, doesn't mean that you have to. If you are going to adopt Brook to manage microservices in your architecture, your ops team may have already invested in RabbitMQ. That shouldn't stop you. So we want that abstraction layer to cover all potential plugins to this growing ecosystem. We also give you the ability to directly pass messages and store state nets for local development and testing, and continue to be able to iterate very quickly when you need to make changes to your system. We do this through behaviors, right? Extensibility allows those event drivers and the storage adapters to adhere to a well-defined contract that either puts data into a storage solution or sends and receives messages back from that log. So coming soon, I am actually working on a Brook Postgres storage driver right now, hopefully in the next week or so. And then eventually, once that pattern is in place, we want to split the library up so that you don't actually have to pull in a bunch of dependencies you're never going to use and minimize the footprint. So Kafka and Redis would be additional dependencies that you'd add if you needed them. So the next component is event handlers. So this is implemented in another behavior. It's a single callback, handle event 1. And the handler module is past all events. Again, every component that is subscribing to the shared conversation of events between the different parts of your service, they're listening and seeing all of the events coming over the wire. But they use multiple pattern match heads of this handle event 1 to determine what is important to them, and they discard the rest. It actually comes baked out of the box. There's a using macro, you pull it in, and it comes out of the box with a universal discard all. And then you just add what you need, and you can match out like, oh, this particular component only cares about, let's say, things coming from this previous application. So author, I'm going to match out author and validate that in a guard. Or events that have only happened within the last 5 minutes, matching on the timestamp. And let your imagination run wild about how granular you can get to target those events that are important to a given component. And we also give you some accessors to the view state because we found that you're storing context in this state for a given application component, and some of that might be relevant to retrieve when it sees an event it needs to act on. And so we actually have a cache built in as well that stores it in memory in ETS, and it allows the application, if it needs to, when it sees an event that it's acting on, through the body of that, before it gets to the end of that handle event block, it can make multiple queries into its own view state cache. And then once it's finally finished evaluating that operation, it will write that back to the persistent store in a transactional fashion. So we also broke out the serializer early on because we found the need to implement the protocols in a data structure library. It was solely dedicated to data structures. And because we want to prioritize structs over less enforceable types for our messages, you need to implement the Brook serializer and deserializer protocol for your custom structs. And one of the things we give you to make that worth your while is, we're serializing everything to JSON when we send it over the wire and when we store it. And when we do that, we're going to match out the struct type. We're going to inject that in a _ Brook struct key into your JSON blob. And then when we go to deserialize that on the other side, or when we are rehydrating that from state, we will check to see, is the module that's indicated in this key loaded? If it is, call the struct function and immediately get it back in the form that you're expecting. Now, maps will still work, but you should be aware that if you send an atom-keyed map in, you are going to get a string-keyed map out, and that's by design. And again, this is a separate library to minimize the footprint depending on how your applications are designed. We also give you out-of-the-box support to serialize and deserialize all of the basic data types that come bundled with Erlang and Elixir, and all of the built-in structs in the Elixir core library. So you only have to do them for the things that you are customizing yourself. So to give you an example, right, here's a very, very simple view of sort of the application that prompted all of this. Is we have a larger system here. We have a scheduler that does cron operations. We have an admin API for interacting with the system. We have an ingestion component that retrieves data from over the network, from out in the world, and decodes it, sends it to a loader and to a broadcaster. The loader will send data into the persistent store, and the broadcaster will send it out over Phoenix WebSockets. And all of this stuff is being coordinated over this event stream in the middle. So to give you an example, right, it's time to do a job. And so the scheduler fires an event into the event stream. So ingest now is going to handle that event. It's going to start reading and decoding data from whatever source that it needs to based on the details of that scheduled task. And as part of that start operation, it's going to fire its own ingest start event into the event stream to let the rest of the system know, yes, I have successfully started scheduling this task. Now, other services may or may not respond as needed at this point. Maybe we are providing stream resources to the downstream components, and so they can start working right now. But maybe we're just buffering it, right? We're going to wait until the entire ingestion is completed, regardless. But the next thing that happens immediately is that ingest is going to actually handle its own ingest start event. Why would it do that? We have a very, that feels terribly inefficient, right? But because we have designed the API to rely on and give a lot of safety guarantees to how this application stores its state and its view of the system as a whole, the snapshot of its current operations, we want the application itself or the component itself to have the same API for interacting with that view that all of the other components are. It doesn't get special treatment. So what happens is that because we have a lot of different, it's a multi-tenant system, and you have lots of different stakeholders who are firing data into and ingesting it at any one time, we schedule all of these jobs with dynamic supervisors, which if you've used dynamic supervisors, they're fantastic, but the problem is as soon as they die, they lose all of the state of the children they were supposed to be watching. And so what we've done at the beginning of every component's boot process is we have an init function task that immediately reads out of view state for that specific component, says, what was I working on when I last died? I should restart these jobs, and that's why we are handling our own events in each of these different applications. So let's say ingest is finished doing its job. It fires another ingest stop event into the event stream, and other components may respond now. So let's say we were buffering and we weren't going to start loading and broadcasting until now. Now it's time for them to do their job. So they're both going to stand up and subscribe to a Kafka topic, let's say, or they're going to requisition additional resources, or they're going to fire up their dynamic supervisors and schedule children and all that jazz. And ingest is going to handle its own event to remove that job from its view state. So when it dies again, inevitably, as we learned yesterday or reminded ourselves yesterday, failure will occur, and we don't want to re-ingest again when ingest fails, when the ingest service fails. So we want to allow it to forget that particular task by handling the event that the others took some completely different action based on. And so now we have, load is going to handle start and stop events from ingest, and it's going to fire its own load start into the system to record that it's doing work and maybe notify other dependent services that it's doing work. Maybe they should get ready. And because this is an event stream and they're both dealing with the same data, and it's now intended to be the same data, it's all decoded to the same thing, broadcast can handle the same events and do its work simultaneously. And it's going to do the same dance to store in its own particular little corner of persistent storage that I'm working on this particular task, and I need to be able to come back to it. And meanwhile, you've got other things going on in the system, like admin's been listening to the entire conversation the whole time, and maybe it's providing you with some capability to introspect the system. Live view is a great use case here to give you real-time visual updates on the progress of everything that's going on. And you can imagine other things like schedule and load could coordinate pausing a data feed for a given table to say, hey, my storage is getting very inefficient for this particular group of data. I need to pause. I need to compact the table. These are all implementation details for our particular storage solution, but I need to compact the table so I'm taking up less space and my queries are now more efficient going forward. And then I can unpause. And I can do all that safely because I'm notifying the system what I'm doing, when I need to do it. Same thing with broadcast, right? Maybe it needs to schedule up to meet more demand. We have additional subscribers coming online, and it needs to requisition new resources. If we're running in Kubernetes, maybe it's going to take operation in conjunction with some operator. And so we have this continual loop of messages coming and going through the system and feeding into and out of each other. It reminds me sort of this. If anybody is familiar with Mr. Chunks, RIP. But we've got some limitations. Like, this is not a perfect solution. We're still working on it. So one of the things that we haven't run into as a problem yet, but it's a theoretical bottleneck, is that we have each application or each component is implementing this handler module for itself, and we're basically single threading the pattern match of events from top to bottom. And as your application grows in complexity and the number of events it has to handle or the number of specific details of an event that it needs to key off of, that could theoretically slow down. But I would also encourage you to think about if that's a good opportunity to break that service into smaller components. It might be doing too much, and that's why you have so many details that event has to be aware of and be ready to handle. So I mentioned some issues around versioning structs. As an efficiency measure, early on, we tried using Erlang's term-to-bin storage solution, which if you haven't tried it, it's fantastic, usually. But because we have microservices that are long-lived and we're deploying this into a production environment, we're making changes. This is emergent architecture here at its best. And maybe we need to change the structure of an event. And maybe a particular event for a particular data set was stored at one point and it's stayed there for a period of time, and in that interim, the structure of that event has changed. And so as soon as that scheduler, say, fires an event to say, call up this very specific data set with an old version of that struct, that blows up immediately. So that's another reason why we like to serialize to JSON, is because it gives us the runway to safely decode that message back into its Erlang term and take necessary operations, so build migration paths into the system to say, and versioning, actually having like a version key in your struct is also important. So you can say, hey, I expect this version, I'm getting this, but I know ahead of time this is the changes that went from version 1 to version 2, and I know how to convert that event to make it compatible with the current version 2. We're actually doing this right now. Special thanks to Chris Keithley's norm library for making that very simple. I encourage you to check that out. Another thing to keep in mind is your event dependency graph. It takes planning. And we're currently limited on the plugins we offer because we've got other things to do. and we're moving fast. But again, Postgres is in progress. I eventually envision Elasticsearch and or MongoDB. Again, we're providing a very specific API, and we sort of encourage you to adhere to that. So it's not so much to give you the special capabilities of interacting with your data based on your storage solution, because in an ideal situation, things are working well, and you never have, that is an abstraction detail you don't have to consider, but it does give you the flexibility to say, hey, my team already has this tool in place. I don't already have Kafka. I don't already have Redis. That shouldn't stop me. And again, for the event bus itself, RabbitMQ is the next planned one, but I think something like Redis PubSub and like a NAT streaming server would be a really good addition to the ecosystem. And finally, to sum it all up, why should I care? We're dealing with, we'd love to deal with these very simple applications. We don't want to deal with the complexities of deploying microservices or versioning them. So why? Why is it good to keep this in mind? Well, companies are moving toward microservices increasingly, and maybe you need them. Maybe your team has the size or the complexity requirements of your problem that it just makes sense. And maybe your CTO just thought they sounded cool, and now you have to deal with that. And these are both realities that you could run into. But it also enforces a contract between your components. And it makes it very easy to reason about how they're going to interact once you sort of get the framework in place. And at least in practice, we found that after we've reached sort of a critical mass of the way a subset of our applications interacted, it was very easy to add new ones without the same growing pains that we had in the early days. So your system will usually tend to calcify into a way that new features will just slot in with increasing ease, especially as you take services that were simple and grew complex and then break them apart again into smaller components. But also this contract eases testing. It makes it very easy to continue to grow your system and have your teams continue to work in parallel and not slow each other down. And that's it. That's all I've got. You can find me on all of those things under that username. You can email me there. And everything that we're working on, the team that I'm on, has sort of been distilled into this, this project in this GitHub organization called In Hindsight. It's a little pun about, we went down a rabbit hole and we learned a lot of things. And we kept saying, well, in hindsight, we would have done it differently. So when we did do it differently, we named it Hindsight. And that's all I've got.